If we wanted to calculate the area under this graph, we could use this little fancy expression here, but what does that even mean? And why is that equal to the area under this graph? Well, let's start with the shape we actually know how to calculate the area of. Let's say rectangles. So let's start by drawing some rectangles under the function with a width of delta x and a height of the function at some x value. We'll call it x sub a. And if we do that, we can just sum up the areas of each individual rectangle and be left with the area under the curve, right? Well, the area of each rectangle is f of x sub a times delta x. So that fancy little expression there just tells us that we're summing up the areas of each rectangle. And this sum is approximately the area under the curve. But wait, there's a bit of a problem. See those gaps of area under the curve that are not accounted for? This would be an underestimate of the actual area under the curve. But how can we fix this? Well, we can just increase the number of rectangles, right? Let's try that. And as you can see, increasing the number of rectangles makes our estimate of the area under the curve more and more accurate. And as the number of rectangles that we use approaches infinity, so the limit as n, the number of rectangles, approaches infinity, our estimate is closer and closer to the actual area under the curve. This is called a Riemann sum, and this limit expression here means the same thing as that little squiggly s expression from before. The s just means we're summing up every combination of f of x, which is the height, times dx, which is an infinitesimally small width, from 0 to 2. An infinite amount of rectangles with an infinitesimally small width. Awesome.